Hello ma'am, I am Pradipta Burman. Along with Navajyoti Bora, we are presenting on entropy and the applications of entropy principle. I was curious to know about why ice melts and why not water converts into ice on its own. After a few research, I came to know about a term called entropy. Hence, I drove down to understand the concept of entropy. I came to know that entropy is something which gives us an overall view on why a physical process go in one way and not the other. So, what is entropy? Entropy is the measure of randomness in a system. Here, randomness means disorder. To get the idea about randomness, we can imagine an organized room and a disorganized room. The image on the left hand side shows the items in the room are less scattered and hence the items are not placed randomly anywhere. Everything is where it needs to be. The probability to find any item in such a room is very high. Since the randomness is less, we can say that the entropy of such a room is less. On the other side, the items in the room are scattered and we can say that the items are placed randomly anywhere in the room. Hence, the probability to find any item in such a room is less, and thus increases the entropy of the room. We can conclude that the entropy of the disorganized room is more than that of the organized ones, because the randomness is more in the latter ones. This is Rudolf Clausius, a German physicist, the originator of the concept of entropy. He used the term entropy in thermodynamics in 1865 CE. The entropy of solid is less than that of liquid, and the entropy of liquid is less than that of gas. The order can be represented as: this is a Stirling engine, where heat is used to do some kind of work. When we use heat to do any kind of work, some amount of heat gets used and other is left as wasted. The waste heat is basically related to entropy. Hence, we can describe entropy as a thermodynamic quantity representing the unavailability of a system's thermal energy for conversion into mechanical work, often interpreted as the degree of disorder or randomness in the system. As heat is associated with entropy, we can measure change in entropy delta S as rate of change in heat energy delta Q with respect to temperature T. Entropy principle. To understand what is the principle of entropy, it is important to know that in thermodynamics, the universe is considered as the summation of system and the surrounding. The universe is considered as an isolated system where there is no mass or energy interactions in and out of the universe. Here we can see particles of two different gases. When the separating boundary is released, the gases tend to mix and increase the randomness of the isolated system. This further increases the entropy of the system. The eighth corollary of the second law of thermodynamics, or we can say the entropy principle, states that the entropy of any closed system which is thermally isolated from the surroundings either increases or, if the process undergo by the system is reversible, remains constant. In other words, the entropy or the randomness never decreases. Hence, it can be clearly stated that Change in entropy of an isolated system is always greater than or equal to zero. Entropy of an isolated system always increases and becomes maximum at the state of equilibrium. Change in entropy is always increasing for the real universe, since there is no reversible spontaneous process possible in nature. Application of the principle of entropy. We can broadly say anything happening in the universe spontaneously is due to entropy. The application of the principle of entropy ranges from melting of ice to the expansion of universe. The principle of increase of entropy is one of the most important laws of physical science. It is the quantitative statement of the second law of thermodynamics. Application 1. Transfer of heat between two thermal reservoirs. Let us consider a steady state heat transfer from a hot reservoir at the temperature Th to a cold reservoir at the temperature Tc through an intermediate body connecting the reservoirs as shown in the figure. Let Q be the rate of heat transfer. It is to be noted that the temperature of the thermal reservoirs remains constant, and that of the system is isolated. The change in entropy of the hot reservoir ΔSH is equal to minus Q by Th. The negative sign is because of heat is transferred from the hot reservoir. The change in the entropy of the cold reservoir is delta Sc, and that is equal to plus Q by Tc. The entropy change of the intermediate body is zero, since it neither gains nor loses heat under steady state conditions. For an isolated system comprising of reservoirs and the rod, and since the entropy is additive, therefore delta S equal to SH plus SC, or delta S universe is equal to delta SH plus delta SC, and that can be written as such. Since Th is greater than Tc, therefore from the previous equation we can conclude that delta S universe is greater than or equal to 0. That is, change in entropy is always positive. Entropy always increases. Thank you, ma'am. My groupmate Navajyoti Bora would be taking over from here.
Hello, ma'am. This is Navajyoti Bora as the groupmate of Pradipta Burman for the group assignment of Test 3. Continuing with the applications of entropy. So, the next application is transfer of heat between a finite body and a thermal energy reservoir. Let us consider a finite body with temperature T and a thermal energy reservoir with temperature T. The temperature of the reservoir remains constant. That means no matter how much heat is added or taken from it, its temperature is constant. To visualize the ocean, no matter how much water we take from it or give to it, the amount or the level stays the same. Not exactly, but approximately. Similar is the case in this with this TER. Okay. We also take that the temperature of the finite body is greater than the temperature of the reservoir, so that heat transfers from the finite body to the reservoir. Now, the transfer of heat takes place from the finite body to the reservoir to the point when the temperature of the finite body becomes equal to the temperature of the reservoir, that is T0. And at this stage, when the temperature of the finite body and the temperature of the reservoir are equal, the transfer of heat stops. Okay. And we also take that the system is insulated, that is, no heat is lost into the surrounding. Now, what do we have to do here? We have to check the entropy principle, which states that the entropy of the universe is always increasing. So, by applying the entropy principle, we have entropy of the universe is equal to entropy of the system plus entropy of the surrounding. As we have taken that the system is insulated, so therefore there is no heat is lost to the surrounding, and so the entropy of the surrounding is zero. Okay. Now we take the finite body as A and the energy reservoir as B. So we are left with entropy of the universe is equal to entropy of the system, which is entropy of the body A plus entropy of the body B. Now we take that the body A has mass m and specific heat C. The specific heat of the energy reservoir is infinite, so we are not writing it here. Now the entropy of the body A is dq by T and the entropy of the body B is q by T naught. Now, as the temperature of the body A of the finite body is varying from T to T naught, we write dq as mc dt and integrate it from T to T naught. So here we have this integration T to T naught mc dt by T plus q by T naught. And since heat is added to the body B, that is to the reservoir, so we have heat that is q, that is positive, q by T naught. Now we put the formula by applying formula and putting the limits, we have this as mc natural log T naught by T. So we get the entropy of the universe as the entropy of the system, which is equal to this term and which is positive, as we can see it clearly. Therefore, entropy of the universe is greater than zero, which is in terms with the entropy principle. The next application is process exhibiting external mechanical irreversibility. Here we have two parts. First is isothermal dissipation of work. We have a resistor with resistance R and a current I is flowing through it. Now this is a control volume. This is the system, the resistor system, and this is the surrounding. Now as current passes through the resistor, heat is dissipated into the surrounding as dq. Now we take the surrounding temperature as T0, which is constant. That is why the process is isothermal, and dissipation of work means that the heat is released into the surrounding. Okay. Now since heat is added to the surrounding, therefore entropy of the surrounding is dq by T. And dq is positive since it is added. Now here, this dq is the time rate. That is, it is the rate of change of entropy. Its unit is kilojoule per Kelvin second. Now what about the entropy of the system? Right? Now, whenever current flows through a wire, it is in steady state. And at steady state, change in entropy is zero. Therefore, entropy of the system is zero. So now we have entropy of the universe is equal to entropy of the system plus entropy of the surrounding. Now since entropy of the system is zero, therefore we have entropy of the universe equal to the entropy of the surrounding, which is nothing but dq by T, and this is clearly a positive quantity. Therefore, once again, it is in terms with the entropy principle.